This problem talks about a long rod of 60 millimeter diameter, and it gives the density, the heat capacity, and the thermal conductivity. It's initially at a uniform temperature and is heated in a forced convection furnace maintained at 750 K. So what that means is our T infinity is 750 K. The convection coefficient is 1,000 watts per meter squared K, and what we are looking for is the center line temperature of the rod. So that's T, the temperature, at 0, R equals 0 at a time when the surface temperature is 550 K. So the first thing that we have to do is calculate the Biot number. So if we look, Bi equals our H and R over 2 divided by K, and when we calculate that, we come out with 0.30. So that's greater than 0.1. We can't use lumped capacitance. So we go to our exact or approximation of the exact solution for an infinite rod. So if we were to look at what that solution is, it equals T, that's our T that we were given for the surface, minus T infinity over Ti minus T infinity. And that's the original description of what theta star is. But we were able to solve that using our exact or our approximate solution so that it's equal to theta sub 0 star, the Bessel function of our eigenvalue times R star. So what we're really looking for is this T at R equals 0. And what that should be is theta star sub 0, which is equal to C1 exponential minus E1 squared times the Fourier number. And if that's what we were looking for, why don't we just solve it right now? And the answer is that we don't have a time, so we couldn't solve for the Fourier number, and we don't have our T initial, because this, again, by definition, is T at 0, so that's your X, minus T infinity over Ti minus T infinity. So instead, let's see if we can make some substitutions so that we don't need time and so that we don't need T initial. So let's go back to our original definition of theta star. So theta star, again, equals T R0 T0 minus T infinity over Ti minus T infinity. And this equals, now we're going to substitute into here T at 0, T, minus T infinity over Ti minus T infinity times that Bessel function. So what that allows us to do is cancel those out. And so what we have now is that T at R0 T0 minus T infinity equals T at 0 T0 minus T infinity. And this is multiplied by that Bessel function times the eigenvalue times R star. So we are given this because it's the surface temperature. We are looking for this. We know what T infinity is. So the next step is to try and find this eigenvalue. So it's in the table, 5,1, and we look at it under our Biot number. Remember, though, the ones that it's calculated for, it's not R outside divided by 2. It's R outside radius. So when we calculate this, we end up with 0.6. So then we go look at table B4, and we look up, first we look up in table 5,1, the eigenvalue, and that equals 1.0184. So our next step is to find the Bessel function of this 1.0184 times R star, which is 1. So let's do that. So now we go to table B4 and look up our Bessel function of 1.0184, and it's approximately 0.7568. So we rewrite, let's take a look at this back here. We rewrite this equation here. We rewrite it in terms of what we're looking for. So our T at 0, T naught, equals T infinity plus 1 over the Bessel function of our eigenvalue, T of R0, T0 minus T infinity. So this is that surface temperature, which is 550 K. And so when we put in our values, which equals 486 K. So the things to remember about this is sometimes you have to go back, as I did, to the original expression for what theta star actually means in terms of temperatures. And in this particular problem, we were missing both the initial temperature as well as time. So we had to figure out a way to cancel out not only T sub I, but also the Fourier number.